As Miller described, in the early 1960s, Bernie Mills left CSIRO and went to the University of Sydney. And the incentive to him going there was they would build a large Mills Cross. So that was, this is the artist's impression, which makes it fairly clear what they're aiming to do. There are two arms, each arm is a mile long. The east-west arm is in two halves, and it rotates about a horizontal axis. If you phase up the arm uniformly, you get a fan beam in a meridian, and you can create a set of fan beams, 4 or 5 on either side, by a small delay gradient down each arm. The north-south arm is just one full section, and it has a problem that you're well aware of, finding a way of, if it's uniformly phased along the arm, you get a fan beam straight up. And if you want to track anywhere else on the sky, even in a transit mode, you have to be able to drive that fan beam in the north-south direction. This is a view of the array after construction. I show it really, there's a range of hills here that sort of shields the telescope from Canberra, which is about 30 kilometers away. So this was the ambition, 400 megahertz, roughly 2-3 arc minutes in resolution to paraboloids. And so they did create a number of fan beams on either side of the central one to improve the efficiency a little bit. So roughly the chronology, in the early 60s it was built and it operated for 25 years or thereabouts. And at that point it sort of covered the sky. It's a fairly inflexible instrument. It's basically just a transit instrument. Once you've done the sky, it's done. So the idea was to move it up, doubling the frequency to 800 megahertz, and also to make it a fan beam array. So this was a synthesis type telescope that they were planning to do. And that took about 5 years or so to implement the hardware upgrade. And my involvement was at the point where all that hardware was in place, and I was involved for about 6 months in the commissioning. So the instrument stayed in that mode of fan beam synthesis for 10 or so years. They upgraded for another 10 years. They were able to synthesize 5-degree fields in each night. Since then, it's gone through an experimental mode for a while, and then now it's in this mode where there's a GPU essentially attached to all of the 150 element bays on the east-west arm. So it's now largely a high time resolution instrument looking for FRBs and pulsars. Okay, so this is the construction of the original cross, and these are the units at the focus line focus of the east-west arm. You can sort of just see the axis, the strong beam at the center that supports that paraboloid, and then these units, these boxes, sit on the posts and form the focal line for the array. You can just see one of the dipoles there. Each of this is I think there are 2 cavities here resonant at the 408 megahertz, and the dipoles just plug straight in. Slight bit of history, there's this folded dipole here. The intention was also to have a 128 megahertz operation. It failed, I think, probably largely for lack of interest. I mean, there was too much to do just getting the 408 working. But it also failed because of the bird life in southern New South Wales. You can see there's a transmission line here for the feed. And there are little plastic spacers going every sort of 50 centimeters. And the birds would remove them about as fast as we could install them. It was probably the holiday treat on the Sunday. Anyway, so this was the way it was installed. It was very simple labor, probably not safe anymore, but it was done. And that's, so this is the completed arm, the east-west arm. Oh, I hit the wrong one, sorry. There you go. So that's the north-south arm. It's a sort of giant chime almost. It's just one straight mile. I'll come back to it a bit later. So the issue that was faced by Mills when he decided to make this conversion from the Mills cross to the synthesis telescope, so doubling the frequency to 840, the north-south arm was abandoned. It was going to be entirely the east-west arm with essentially 150 independent bays on this east-west axis. instead of having linear dipoles, they elected to go to circular polarization. And this was quite a clever idea because it allowed them to get differential phase from one dipole to the next. If you've got a helix, the first one rotates 1 degree, the second by 2 degrees, 4 degrees, and so on. And you can get a phase gradient along each bay on the line focus. So that was the reason for going for the helices. It was a much simpler way of getting a phase gradient, the phase gradient you need within each bay if you want to steer the fan beam off the meridian. So that's what I'll describe a little bit more, but that's the essential engineering change they had to make. Having abandoned the north-south arm, they have to make the east-west arm able to tip around the horizontal axis for elevation, and then for azimuth, essentially you steer the fan beam away from the meridian. And then you have to provide a delay between each bay to make the delay linear along the full length of the arm. The data processing was with analog beamformers, and you observed for one night, 12 hours rather. And at the end of those 12 hours, you had a map about 1 degree square. And at a much later date, it went up to 5 degrees. So that's the problem we have to resolve. And the essentials of how to do this was actually developed on the north-south arm. So the idea was, within each of these bays, between those two posts, you've got a whole set of dipoles. And the idea was, within each of these modules, between those two posts, in effect, you had a transmission line made of 2 parallel plates. And between the 2 plates, you had a helix for each dipole. Helix was about that long. And the coupling between the helix and the parallel plates effectively depended on where the helix was horizontal. And so you rotate the helix and you can move the coupling point along the plate. So every dipole was coupled to one of these. And there are something like 35, 36 dipoles within each module. And each dipole has a different gear ratio to the main drive. So the reason I talk about this is, if you were thinking about it, you'd say it's just not going to work. You have one drive shaft which runs the whole mile with a tap-off point on every module to another drive shaft. And then on that drive shaft, you have 36 spur gears, one for each dipole. And to think that that's going to survive summer and winter, night and day, did seem a bit improbable, but it worked. Now, in the Mills Cross, you set up once each day when you were doing your observing. You'd set it up for a particular elevation, and then you could leave it. In the next, well, I just already said most of that, so go to the next. In the new version, on the synthesis telescope, that tracking has to happen during an observation. So now you're moving those gears far more often. So this is, instead of the linear dipole they had at 408, it's a helix. It's a very flattened helix, but it's a helix. So that gives us a circular polarization. So now the phasing is to rotate each helix by differentially a different amount, 1 degree, 2 degrees, 3 degrees, 4 degrees, to get your gradient. And so that's the gear. Each one will have a different size gear to give you the grading as you go down the arm or down within the module. And that's just another view of the helix. Okay. This is the focal unit. The helices are hidden behind these flower pots. And the axis of each helix just goes straight through to that box where you've got all the gearing. So this is a nice little compact unit. And this is, again, now the east-west arm with the helix mechanic working where the gears up there. So that is essentially the solution. And that's what they were able to achieve after this upgrade, that you've got an impressive collecting area. From the point of view of synthesis, it's incredibly redundant. I mean, there are 144 modules, all equally spaced, and every one has a separate IF coming back to the central site. So, you've got immense number of duplicate baselines, and it's a fabulous coverage. So the resolution was 40 arc seconds, roughly. And it's this combination of mechanical steering to rotate about this east-west axis and the electronic steering, all those little gear wheels. I guess I should call it mechanical steering. It took after 12 hours, you had a beautiful image with this 40 arc second resolution. So that's what, instead of, okay, I'm just about there. If you created one linear gradient of phase and delay along the arm, you've got one fan beam. Now, within that beam within the beam of each module, you've got fairly wide tolerance. So you could create a nest of fan beams within that primary beam. And they created, in fact, 77 of them. So 77 gives you the 1 degree field of view. So that's the fan beam. The beamformer. You've got all the 144 cables coming in, and you combine them in the right way, and you get 77 beams coming out. What I should just go back a touch. In the processing, every integration period, you'd sample all 77 beams, and you have an amplitude for each one, and you'd start with a black array, the field of view. And for each integration, you've got the hour angle where it is on the sky, and you'd lay down on the map the amplitude of that fan beam, and then the amplitude of all the adjacent fan beams. So over the course of the 24 hours, or 12 hours, all those fan beams would have rotated, and any point within that field of view will pop up in the right place, as that image was showing. Okay, so it gives you a quality image. It's a genuine census image. It just took 12 hours to obtain. So this was the mode in which they operated, 1 square degree field of view, and they ran that way for 5 or 6 years, I think. And then they applied a rather more advanced technology of beam forming, and they were able to expand to 5 square degrees per night. Within 30 seconds of finishing, so I guess I showed that not quite a typical field, but a good one. And the interesting thing for a reason it was chosen was that was a supernova 87A, and they've been observing it for the last, I think, continuously. This was just taken 12 years since the explosion. And then finally, the current state, it's gone through yet another evolution. There's a massive number, it's like CHIME in effect. So there are a massive number of GPUs, one for every bay, 144 of them, and it's being used as a high-time sensitivity, high-time resolution instrument looking for pulsars, looking for FRBs. And that, I think, is it. Yep, thank you.
What can you tell us about the three FRBs that were mentioned in Nature having been found by Matthew and his gang?
No, I'm afraid I know no more than, in fact, I know even less. I hadn't seen that. I was told just before I left that, yes, he just found, they switched on the GPUs, and next night there was an FRB pretty much. It's a very powerful, I think Matthew, for what it's worth, the previous 4 years, they had struggled to build an FPGA version of what Matthew implemented. And that was a struggle, new technology or whatever, whereas Matthew had been playing with GPUs for a while. And he rolled in his team of 25 very bright students and 500 GPUs and 148, I guess.
And what about the Adam Deller plan to use the north-south arm for FRB? Do you know about that?
No, I don't. It currently is set up for 408 megahertz, so I'm not sure what they do. But yeah, or we could just sell it to Chime. I mean, it's right shape, at least.
I had a question. We heard yesterday that 10.7 megahertz had a very specific origin. I've wondered and been asking around for months, where did 408 megahertz come from? I thought this is the right group of people to ask. Why 408?
Well, Mills had worked at 80 megahertz and he'd done the sky, so he had to go to the next one up.
Why not 400? Why 408?
Oh.
I'm sure it was allocated
Is it out
in the 1950s, probably.
Okay.
Yeah.
So it's
But
just
why
allocated.
specifically 408, I don't know.
Okay,
I think Bernie Mills had a transmission license at 408.
at 408. Okay, that's
That's what he told me.
there's your answer.
I think it's not radar. You know, it's not World War II. I think it was just an open few megahertz.
Okay,
It was an open band.
okay, perfect, thank you.
I know how Cambridge got 81.5 megahertz for one of their arrays, 2C.
Well, Mills, the original Mills was 81.5.
Yes, well, I don't know if that followed the Cambridge frequency or not, but anyway, 81.5 came about because Martin Ryle told Tony Hewish, cut the dipoles for 80 megahertz. And Tony cut them all wrong.
I doubt if.
All right, one very quick question if there is one. Okay, well, let's thank Mike.